In this lecture, we'll be covering the analysis of a very simplified PCB model, basically seeing the effects of temperature gradient or heat transfer through the PCB to the structural deformation of the model. And because of the complexity of this model and the amount of time it takes for modeling, I have created a script here that I will go through line by line and explain what each line does. And then later we'll do post-processing of this model. So the first 4 lines are basically finishing whatever we were doing and clearing the database title. And in this line, I've defined a parameter called ratio to convert between meters and millimeters. And between lines 8 and line 23, I have defined some parameters to use for geometry or creating the solid model. And that's because I will refer to these numbers frequently in my solid model creation. And in case something changes that I need to change, say, for example, the radius of the solder ball or the pitch or the width of part of my model, and due to multiple references to these numbers, it would be cumbersome to change those models if I did not use a parameter for my solid model creation. That's why I've used these parameters or defined these parameters here based on the dimensions of the PCB, so that again, if something changes, I can just change one value here and everything will change accordingly in the solid model creation. So the radius, the pitch, and the height of the ball, the width and height and the thickness of the PCB, and the substrate, basically the width, length, and thickness, and the same for the width, length, and thickness of the molding compound on my electronic packaging device. Here I've used 4 parameters. I've defined 4 parameters which I'm going to use as the numbers or the values for the material models that I will define later in my analysis. And that's because I have multiple materials, and if I want to pick elements by material model number, I may not remember what number I used for the PCB or the substrate. But by defining a material, or by defining a parameter which I can remember, for example, stop mat or MLD mat, I don't need to remember the number I picked for these material models. I will just use the parameter and ANSYS will figure things out automatically. And then I start pre-processing by using this \prep7, and I define an element type 200. So this is an interesting element type. If I take a look at that in help topics and go into element references and find element type 200, which is here. So element type 200 is an element which is for mesh only. It does not have any degrees of freedom, doesn't contribute to the solution, and basically is, let's say you have an area and you want to mesh it and import that mesh or incorporate that mesh in meshing a volume that you create by extruding that area. Or if you have a line and you want to use those lines or meshing of a line to create areas, you can use mesh 200. And don't worry if it's a little bit vague, the explanation of this. You will see what it means as we go through this example. And then there are key options for element type 200 to determine its initial shape. So I've used key option, I've set key option 1 to 7 to use this shape for the 2D meshing of areas that I want to import in my volume extrusion to create the volumes as I do this or create the solid model. So, and the number I've given, as in the reference number I've given for that is 200. So I'm using the same number as the element type, and it's the reference number is basically arbitrary. I can pick any number, but just so I remember what element number or reference number I used for element type 200, I picked the same element type. And here I'm giving the value for key option 1. There are 2 ways to do that. One way is to put comma after the element type and then put the value for the appropriate key option. So this is key option 1, so I put just 1 comma and give the value 1. Or the most comprehensive method of doing it is use key opt command for element type reference number 200, key option 1, and the value is 7. Next thing is I'm using element type 226, which is a higher order 3D coupled field analysis element type. And because I want to use thermal and structural, I set the key option 1 to 11. And I don't need a real constant, so I just leave it blank as is. And here I've defined 4 material models. The first one is the material models of the substrate. So I've used Young's modulus, Poisson ratio, and coefficient of thermal expansion in X, Y, and Z directions. As you can see, they are different. And the conduction coefficient, which is isotropic in all directions. Then I have defined the materials for the molding compound. Next is the material definition for the solder balls. And then the material properties for the PCB in the bottom of the model. As you can see, like I said before, instead of giving actual numbers, I'm using parameters for as I define the material models. I can refer to these parameters later in my analysis. Then I'm defining a local coordinate system. The number for that is 11. And then it's a Cartesian coordinate system. So let's find the local command in APDL help documentation. Go to commands, under L, find local. It should be here. So the first one is an arbitrary number. The second one is the type of coordinate system. By default is 0, or I want to give a 0 Cartesian coordinate system. And then the next 3 are the origin of the basically the coordinate system in the global coordinate system. So X, Y, and Z are the origins of the coordinate system in the global coordinate system. And then rotating the axis and basically X towards Y, Y towards Z, and Z towards X. By giving values in here, we can rotate the axis of the new local coordinate system. And then by using CSS, 11, I'm using the coordinate system that I defined in line 62 for the rest of my modeling. So if I just copy this portion of my code into APDL and press yes there, I see that nothing actually happened besides creating the local coordinate system 11, and material models are defined. So I have 4 material models. I can click on one of these, for example, and see the values for coefficient of thermal expansion, and also I have element types defined. So a mesh and solid 226. If I click on options for that, I see it's structural thermal. Next, I want to create the solder balls. So I have defined some key points to create the solder ball. So let's just copy the first 5 key points for key point commands and see where they are created. So 5 key points here, depending on the dimensions that I gave before. And then I have an additional 4 key points 6 to 9. Let's see what they do. They create key points on the top surface, which will be the bottom surface of the substrate. Let's take a look at that in 3D. And then I have another set of 4 key points, which are for the bottom surface of the solder ball, which is the top surface of the PCB. So if I copy those lines and put them here, so you can see that key points basically 10, 11, 12, and 13. 10, 11, 12, and 13 are created. Now I'm using these key points to create lines. So let's create the first lines, which are for the solder ball. So those are created. And these divisions that you see there are from here. So the third input for an L command would be the number of divisions on the line. So I've put 8. Then I'm creating 4 additional key points for the bottom surface of the substrate using the L command. Those are there. And then I'm creating another 4 lines for the top surface of the PCB. And if I look from the side, you see that if I do Lplot, see that those lines are on the same plane of the top and bottom lines of the solder ball, respectively. Now I want to use LE size for the first line, which was the arc, and divide it by 8 segments. So if I do that, so all of my lines are divided into given number of divisions. Now I want to create an area and then rotate that area to create a volume, and use the CM command to call that volume a name, which I'm calling it a solder. So if I do this, paste it there, see that the volume is created. Now I want to divide the additional lines that I created, that were created here. So if I do Lplot, you can see that there are some lines which are not divided yet, which are basically the additional arcs. By using LE size all, I can divide those by 8 divisions as well. And because the other lines are already having their divisions set to them, by using this LE size all, those lines are not affected. So even if I had given a different division number, the lines that were previously divided will not be affected by this command. Now I'm going to create additional 2 areas, which is the top and bottom surfaces of the solder ball. If I do a plot, you can see that I have areas on the bottom and top. Now I want to select the lines on the top surface of the solder ball and overlap them, because right now the rectangle covers the circle on the top surface of the solder ball. So what I want to do is to overlap those areas. Like this. Now if I do a plot again, and if I enable numbering of areas, you can see that this outer area does not include the circle. Let me just turn off the numbering of areas. Now what I want to do is to use the element type 200, which is just a mesh and doesn't contribute to the solution, and mesh all the areas. So I want to do this. It didn't work. Now this area is meshed. And next thing is that I want to define E size and give a number of divisions. Use type 1, which is the element type for coupled field analysis. Real 1, which doesn't do anything. And then mat, comma, submat. So I want to make the substrate and extrude the area, these areas that I've already selected, and the Z direction by the value which is sub thickness, so thickness of the substrate. So if I do this and copy that here, a plot, and I can see that the substrate is created and meshed. So here, as you can see, I did not use a vmesh command at all. I only used vextrude, and also just defined the element size of material and stuff before meshing. I can all cell, and I want to unselect the solder, which I had already used or defined through in line 103, and then call the next one a substrate. The volume is substrate, and mesh it in here, and then I'll do the rest of it. Next, I want to create the volume for the PCB. So if I select these lines, or actually for the molding compound, not the PCB, and what I do is select the areas on the surface, which is ball height plus substrate thickness, and pick the right element size and the material model and real constant material and actually material model is in here, element type, and material model is mold and compound, and extrude that by the thickness of the mold and compound, I can create the mold volume, which you can see is created there. The size is a little bit different. The next thing I want to do is to define or select the volumes, the new volume, by basically unselecting the previously defined volume, solder and substrate, and call the new volume the mold and compound, or mold. So I do that there. That is created. The next thing I want to do is to define and create the PCB. So first I'm selecting areas in the Z direction where the value is minus ball height, and then overlap the areas like I did before, and then pick element type 200, which is only for meshing, and mesh those areas. So if I do that and put that in here, so you can see that those areas are created and meshed. And then I want to use 12 element size divisions, use type 1, which is again 226, real constant 1, which isn't anything, material model PCB matte, and extrude that by the thickness of the plate or the PCB, and do all cell. So I can do this, and I have, if I look from the side, the only thing I need to create is the solder balls. But before that, I want to select the volume and call it PCB. Now finally, I want to pick element type 1, which is 226, real constant, nothing, material model solder material, and then V-mesh the solder ball. So if I do this, see that the model is complete. One thing which is important is to make sure that the elements or the nodes are meeting. So if I look at in here, the elements of the solder ball have their nodes where the elements of the PCB have their nodes. And if I also take a look at here, if I can zoom out and then zoom in here, see that the lines from the substrate are matching the lines from the solder ball. That means the model is actually meshed properly. If one of these lines was ending here in the middle of this line, that would mean that the nodes are not coincident or merged. As a result, the model was not a solid part. So that shows that the meshing has been done properly. Now what I want to do is to copy this entire volume in all directions, or all of them, by the ball pitch and X direction. So if I find the vgen command and the help documentation, vgen, number of copies you want, and then which volumes, I could say all for N1 and then ignore NV2 and NI and C, and then give the value in each of these directions, so X, Y, and Z. So I've given here 2 items, all of the volumes, and ball pitch, which means the distance between solder balls, in the X direction. So if I use that line, see that the volume is copied with all the meshes. So if I do eplot, but the thing is, right now the nodes which are on the coincident surfaces of these 2 volumes are duplicate, which means this is not a one solid part. And what I have to do, and because I have so many nodes in here and it would be very crowded if I wanted to show the node numbers, I skip that section. But what I have to do is to pick the nodes at that location, which means at X equals ball pitch, and do the non-merge. And because of the small dimensions of my solid model, I have to also use a tolerance, so ANSYS doesn't look for nodes which are not actually coincident, and merge them. So if I do this and paste it in here, those nodes are merged right now. The next thing I want to do is to do the same thing. Now I want to merge everything in the Y direction, or copy everything in the Y direction. So I'll have 4 solder balls, and basically this is a very simplified PCB model. And next, again, now I have to define or select the nodes at a certain location in Y, which is the this value, and then merge the nodes so that they won't, that the entire thing would be a solid part. Now what I want to do is to select the nodes at the bottom of this PCB model, and let me do ePlot, and fix them in all directions in space and apply a heat flux. So if I do this and copy it here, so all the X, Y, and Z coordinate displacements are set to 0, and a heat flux is applied. And again, I'm using UX, UI, and UZ instead of doing all, because there's also a temperature degree of freedom for these nodes, which I don't want to set to 0. The next thing I want to do is to apply a convection on the top surface of the molding compound only. So if I do that, if I paste it in here, the convection is also applied, and this is it. And I can just come into solution and solve it. But because this will take a long time, I'm not going to solve it right now. I've actually solved this and saved the results. So basically, by defining static for analysis type and give the sparse, which is a default solver type, and ANSYS. Reference temperature is 32, which means 32 degrees Celsius is where stresses and strains are 0. A time of 1, which doesn't really change anything in a static analysis and linear elastic. And also, and then here I'm solving, and the last line I'm saving the results so I can load them later in ANSYS and do more post-processing. So here we created a very simplified model of a PCB, applied the boundary conditions and the loads. The next lecture we'll do post-processing of this simplified PCB model.